In chapter 1, we learned about the method of science, coming up with ideas, explanations, and then actually testing them to see if the ideas are true. So let's see how that plays out when we talk about Newton's first law. This is chapter 2, Newton's first law on the law of inertia. The things we'll talk about are, well, we'll look at Aristotle's physics. He wrote the book on physics, literally, his book called Physics. So we'll see some of his ideas that were eventually demolished by Galileo and then perfected further by Newton in his first law of motion. We'll look at the ideas of net force or total force and equilibrium. And we'll talk about support force, also known as normal force. And we'll also describe how things can be in equilibrium but still moving as well. So first, what did Aristotle's physics say? Aristotle believed there were 4 elements: earth, air, water, and fire. And depending on what kind of element something was made of, that would determine how it would move, what kind of motion it would experience. For example, Aristotle would say smoke rises because it's made of air and tends to rise into the heavens, into the atmosphere. So he believed there were natural motions. For example, the planets went in natural motion of circles. He believed that circles were a mystical shape and that planets were some divine beings that moved in these perfect circles. Planets, their natural motion is circles. He believed that things on the Earth move depending on what they were made of, depending what elements they were made of. He believed in gravity, the force of gravity that pulls Earth-like things down towards the Earth, and then levity. So gravity pulled Earth and water down to the Earth. Levity pulls things like air and fire up towards the heavens. And then the Earth itself was the center of the universe, and it stayed motionless. So basically, things that were heavenly, like fire and air, tend to go up towards the heavens. Earth and water, those kind of things go towards the motionless Earth. Those are natural motions. They just do that under their own power, I guess. He also believed in violent motions, which are now what we'd understand to be like external forces. In other words, a ball, although Aristotle would say it's made of earth and it wants to fall to the earth, I could throw the ball and apply an external influence upon it and, chuck the ball across the room. That'd be a violent motion. Okay, so these ideas, they were based on philosophy. They sounded good. Aristotle was super clever, but of course he didn't take the step of really testing a lot of these things. So his ideas began to crumble. Copernicus in the 1500s realized that things that Aristotle said were not really true. They just didn't add up to him. Let me show you what I mean. What I'm going to show you is a star map, and it shows where Mars, this is Mars of the cursor here, it shows where Mars is in the night sky over a span of about 6 months. So here's Mars cruising along. It actually reverses its course in the sky and loops around. We call this retrograde motion, and then continues along its path through the heavens. Now, obviously Mars is not moving in some perfect circle in the sky. Aristotle was no dummy. They knew that. They knew the planets did these things, these retrograde motions. So they came up with a clever scheme to explain it. Blue is Earth. Remember, they believed Earth was the center of the universe. Yellow is the sun, and they believed the sun went around the Earth. Here is Mars. Mars goes on a perfect circle. Actually, it goes on a perfect circle with another circle that rolls around on that one. And that can explain how Mars follows this backwards path sometimes as it rolls on this double circle thing. So that was the scheme they had to explain the orbits of the planets, all based on perfect circular paths. Copernicus realized there is a much simpler explanation, more satisfying explanation, which is that the sun is at the center of everything. The Earth and Mars go around the sun. How does this explain the retrograde motion? Well, you see, Earth moves in its orbit faster, and it overtakes Mars. So when Earth overtakes Mars in the orbit, then Mars appears to move backwards, kind of like passing a car. The car appears to go backwards according to you. And then Mars follows this backwards path temporarily as we move in our orbits. So that was Copernicus's revolution. The Copernican revolution is that we should adopt a heliocentric model, that is, a sun-centered model, with the sun at the center of, well, they would have said the center of the universe. Galileo also believed in this heliocentric model. He demolished Aristotle's ideas even further. He was the first to use a telescope to discover some really significant things. He used a telescope, and what he saw when he looked at Jupiter, here's Jupiter, this is from his notebook. This is Jupiter right here. He saw that Jupiter had moons that orbited around it. Here it is from night to night. The positions changed. He understood it to mean that there are moons orbiting around Jupiter. It means that, Earth isn't the center of everything here. There are these other planets that have their own moons going around it. He also saw that when he looked at Venus, this is Venus, he saw that sometimes Venus had a crescent shape to it. Now, why would Venus have a crescent shape? It means that it's going around the sun, because depending where it is in its orbit, sometimes you'll see it a half-lit Venus. Sometimes you'll see a fully lit Venus, or sometimes you might see a crescent Venus when it's off to the side of the sun. So he understood this to mean that Venus is going around the sun. It's not going around the Earth. So he adopted the heliocentric point of view. When he looked in his telescope, Galileo also saw other stunning things. He saw sunspots for the first time. It means the sun isn't this perfect, godlike, unchanging thing in the sky. It has these imperfections on it. He also noticed that when he looked through his telescope at the dark night sky, there were just loads of stars out there that no one knew about before. Suddenly, things got a lot more complicated when Galileo looked through his telescope. He also knew about things like comets, which suddenly appear, and that these comets are way beyond where the moon is. It's not this unchanging heavens with perfect circles in it. There's all kinds of stuff going on that's way more complicated than Aristotle's model would imply. So then you might know the story that Galileo was tried for heresy by the Roman Catholic Church. His ideas, he adopted the heliocentric point of view that the sun is at the center. That means the earth moves around the sun, directly contradicts what the Bible says, that the earth cannot be moved, that it was set in place at the beginning and is not in motion at all. So, that's part of the story. He was tried for heresy for believing in the heliocentric view. Also, the church just didn't like the heliocentric view because it wasn't fully formed yet, and the model with the circles upon the circles was very well modeled and understood, and it gave very precise measurements for the motions of the planets. So the heresy part of it is part of the story. So Galileo's demolishing Aristotle's beliefs that were, believed for like a couple thousand years. Some of his discoveries, I mentioned some with the telescope, the moons of Jupiter, sunspots, all the stars in the Milky Way that he was able to see. But let's focus on some of his other discoveries. He discovered that no matter the weight of an object, they fall at the same rate. So he discovered the law of falling bodies, which demolished Aristotle's idea that heavier things have more earth in them and therefore fall to the earth faster. That's number one that we'll focus on later, actually, in a later chapter. What we're going to look at now is his other discovery, which is the law of inertia. And let's discuss that and what Aristotle thought about it. A force, we need some terminology first. When we talk about a force, what comes into your mind? Star Wars, I think. Force is any push or pull, not necessarily like the force, which acts at a distance, but the force is just one sort of example of that. A force is any push or pull. It doesn't have to be some mysterious thing acting at a distance. If I pull a door open, I'm applying a force to the door. When I throw a ball, I'm pushing on the surface of the ball and I'm applying a force to the ball. Now, inertia is a property of matter to maintain its motion. Even if there's no force acting on it, even without any force acting on it. How strongly it maintains its motion depends on the mass of the object. The mass is a thing you measure in kilograms. What I mean is, the tendency of things is to maintain their motion. Like, think of a football player running along. Difficult to deflect them, to push them off course, right? You can push them off course, but it's very difficult because they probably have a large mass. If it's just a butterfly flying along, it's easy to deflect them off course because their mass is very little and you can, like swat at a fly and knock it off course easily. But the universal tendency of all matter is to maintain its motion. Galileo knew about this, and he did experiments to demonstrate it. His first thought was something like this. He was studying actually gravity and rolling things up and down inclines. He knew that when he sent a ball down an incline, it gained speed. Its speed increases faster and faster. When he rolled it up the incline, its speed decreases. It slows down. Think of like a roller coaster going up a hill, it loses speed on the way up. He thought that perhaps then, if there's no slope, then it should be something in between, neither gaining speed nor losing speed, because it's neither a downslope or an upslope. So that was his initial thought about how things might move. He also realized that, of course, if you actually roll a ball along the ground, it does eventually stop. And what he realized is that the reason it stops is just because of air resistance that'll slow down the ball. So he did some experiments to test it. Scientific method in its infancy here. Doing tests to see whether his idea made sense. The tests went like this. He joined two ramps together so that he could roll the ball down, and he noticed it would always reach a final position at the same height on the other side. So that's the experiment. He could make the central flat part longer and longer and longer, and find that the ball always tended to reach the same final height. So he could make the central part longer and longer and longer, and And if it's extremely long, then where's the final position? The ball tends to come to rest only when it reaches the same initial height. If it can't get to that initial height, it just keeps right on going on the flat portion, rolling right along. So it gave evidence to his idea that the ball will keep right on rolling. That's the idea of inertia, that the tendency is for the motion to be maintained. Through these kind of experiments, it demolished the ideas of Aristotle. You see, Aristotle thought that things like the earth tended to stay at rest. That was their natural state, and that a force is required to get them moving. Any kind of motion, Aristotle argued, requires a force. So Aristotle said continuation of motion depends on continued or continuous application of force. Aristotle thought things didn't just keep moving on their own. Galileo, through his experiments, said, you're wrong, they do. Continuation of motion requires no force at all. A ball will just continue to roll on its own without any force being applied to it. That's what it naturally tends to do. Just keep right on going. Think of like you push a shopping cart. It'll just keep right on going, except that friction and things, that's what eventually slows it down. But if you eliminate friction from the equation, it keeps right on going. Now, there is a common objection to this idea. The ideas that Galileo had. Galileo believed that, the Earth was moving around the sun. And people argued that if the Earth is moving, surely we would fly off the Earth, right? How could a bird jump off the tree, fly off the tree, and get the worm? Shouldn't it get thrown off the surface of the Earth as the Earth is moving super fast? They knew that if the Earth was actually moving, it had to be going at 30 kilometers per second. That's incredibly fast. Shouldn't we be thrown off by it? Galileo proposed the Earth was moving. So why aren't we thrown off the Earth? Well, we're moving with the Earth. We're moving with the Earth. We're already in motion. And the tendency of things is to maintain that motion. Earth was moving, and in fact, the whole population of the Earth is already moving with it. Moving in common motion with the Earth. So you're already in that motion. The tendency is to maintain whatever motion you have. Do you see how this explains or refutes the argument? That if we're already in motion and the tendency is just to maintain motion, then of course we don't fly off the Earth. Another argument he had about this was, look, if you go down below the deck of a moving ship, smoke from incense will just rise straight up. It's not thrown one way or the other. Butterflies beneath the decks of the ship fly back and forth without any extra effort. They don't have to keep up with the motion. When you stand up on a moving ship, you don't have to jump forwards to keep up with the moving ship. You're already in that motion, and the universal natural state of things is to maintain that kind of motion. Now, Galileo believed that whatever the motion was, that's how you continue it. Like the Earth's going, Galileo actually believed the Earth is circling the sun. Okay, so he believed that things do move in circles, and they tend to maintain that circular motion. That's why we don't fly off the Earth, because we're already moving with it. Galileo argued about on a moving ship. What about if you're riding in a van at a steady speed? You toss a coin up in the air. Where's the coin going to land? Pause it, answer the question, and then I'll come back. So you toss the coin up. The coin's already in motion with the van. That means the coin lands right back in your hand again. It keeps up with the motion of the van. It falls right back in your hand again. Notice how it moves. According to you in the van, the coin just goes straight up and down. You can play catch in a van, no problem. But to someone watching on the ground, the van is in motion, and when you toss the coin up in the air, the coin goes up, follows an arc, and lands back right in your hand again. But the van is in motion, the coin is already moving with it, and the coin just maintains that motion. Try it out next time you're in a car. You'll, with no problem, toss the coin up and back into your hand again. Now, if gravity between the sun and the earth, suppose it suddenly vanished, gravity disappeared between the sun and the earth, how would Earth continue to move? In a curve, in a spiral, outwards or inwards, or would it be in a straight line path? In other words, if this is the sun and the Earth going around it, what if gravity ended right at this moment when the Earth's orbiting here? How would the Earth move? Galileo believed that the planets naturally go in circles. They were already going in circles, and they would naturally tend to go in that circle. So Galileo would have said, A, that the planets just naturally do their circling thing. However, it turns out that is wrong. It turns out that if gravity disappeared, the planet will continue off in a straight line path. So Galileo had brilliant guy, had great ideas. He was right about the idea of inertia, that things tend to maintain their motion naturally without any extra force needed. But he had some things that need to be fixed up. This is where Isaac Newton comes along. In the 1700s, he made a number of groundbreaking discoveries. He discovered the laws by which things move. He discovered 3 laws of motion. We're coming up on learning the first one now, which is the inertial law. He discovered a law of gravitation to finally explain exactly why the planets and the comets are doing what they do. And amongst many other things, he discovered many things about optics, like prisms, that white light was made of a spectrum of colors. Huge groundbreaking things that we still use today. So let's put down Newton's first law of motion. Remember, Galileo discovered the law of inertia. The things tend to maintain their motion, even with no force acting on them at all. Think of an ice skater can just glide along on the ice. They just go, they just keep on going. So Newton's first law of motion says that, okay, not only do things maintain their motion, but in fact, what they maintain is motion in a straight line. Okay? So it's often said this way: objects in motion maintain their motion. But we need to kind of perfect it, patch it up so it's really, really correct. And this is what the idea of inertia is about. Galileo already knew that. What's the big deal with Newton's first law? Well, he realized that it's really just straight line motion, that's the kind of motion that's continued. And it is stated this way: in the absence of any external force, a body, a planet, football player, an ice skater, whatever, a body maintains straight line motion at a steady speed. So the ice skater gliding along, her speed's not going to get bigger or smaller. She's not going to speed up or slow down. The tendency is for her to just cruise along. Now, eventually she will stop, but that's not, that's because of friction, like wind resistance blowing against her body that slows her down. So Newton's first law of motion includes both things being at rest. If an object is at rest, it will stay at rest if there's no force acting on it. But it includes more than that. If something is already in motion and there's no force on it, then it will just continue that motion, cruising along steadily with no loss or gain in speed at all. Worth remembering, this totally demolishes Aristotle's ideas that in order for something to keep on moving, Aristotle thought it required a perpetual force acting on it. Question. A ball's resting in the middle of a cart, like a shopping cart or something. When you quickly jerk the cart forwards, what happens to the ball? Is it hit the front, the back, stays in the middle of the cart, or it depends on how quickly you pull it? Take a minute, pause it, think about it. Well, the ball's at rest. When I jerk the cart forwards, the cart moves forwards, but remember, the tendency is for the ball to stay in position. So that means the cart will move forwards, leaving the ball in place, and the ball is going to stay there and crash into the back of the cart. Hits the back of the cart. Let me show you some examples of inertia in action. Here is a famous trick. It's like pulling the tablecloth out from the vase and the vase stays still. Here's a tray being knocked out. The eggs have no force on them, so they tend to stay at rest and they just fall straight down. Here, person on rollerblades, the table can be pulled back and forth underneath them, but they tend to stay in place. With no force acting on her, she tends to remain in position. Here, the leaves hover for a moment, even as the net falls out from underneath them. That's inertia. Here's a giraffe. Why do we wear a seatbelt? You see, when the car stops, our head tends to maintain its motion. That's inertia. Our head is in motion. Our head tends to remain in motion even when the car stops underneath it. So here we see why we wear a seatbelt.